Every morning follows a familiar, reliable rhythm. Ocean waves roll onto the sand, frost settles on the grass, and a gentle breeze moves through the trees. We rely on these patterns to make sense of the world, but data from agencies like NOAA and the Swedish Meteorological and Hydrological Institute suggest that our surface-level observations leave out a much larger story. For instance, we can see the moon's gravity pulling the ocean toward it, yet the data shows a second matching high tide bulging out on the exact opposite side of the planet, facing directly away from the moon. On a cold morning, we expect the sun's appearance to begin warming the ground immediately. Instead, the thermometer often continues to drop to its lowest point of the day, well after the sun has cleared the horizon. Even a light wind is driven by an invisible mechanism. The air around us, which feels weightless, is actually exerting enough physical pressure to shift the course of global weather systems. These everyday events are the visible results of massive, opposing physical forces. They are constantly interacting in the background, seeking a state of equilibrium that the movement of our planet prevents them from ever reaching. On the side of the Earth facing the moon, the mechanics are straightforward. The moon's gravitational pull exceeds the water's inertia, dragging the ocean into a bulge on the near side. However, on the far side of the planet, the moon's gravitational influence is significantly weaker due to the increased distance. Despite this, a second bulge of water forms here, pointing away from the moon. This happens because of inertia. The water's momentum attempts to keep it moving in a straight line, and on this far side, that outward force exceeds the moon's weakened gravitational pull. These two forces, gravity on the near side and inertia on the far side, create two permanent bulges. The solid Earth rotates through this static oval-shaped envelope of water every 24 hours. A high tide represents the moment a specific coastline rotates into one of these regions where gravity and inertia have reached a planetary scale standstill. We see a similar gap between observation and physics at daybreak. It is easy to assume that the sun's first rays bring an immediate net increase in heat to the environment. But as this radiation balance diagram shows, the Earth is a constant emitter of infrared energy. It loses heat to the vacuum of space 24 hours a day, regardless of whether the sun is up. At the moment of sunrise, the incoming solar radiation is at its weakest. For a short period, the amount of heat the Earth is venting into space remains higher than the energy the sun is providing. This thermal deficit is often compounded by turbulence. As the sun begins to warm the ground, the air near the surface mixes with the air a few meters higher up, right where our weather station thermometers are located. The ambient temperature only starts its daily climb once the sun reaches an angle where the incoming radiation mathematically surpasses the planet's outgoing heat loss. The sharp chill of the early morning marks this brief window of time where the planet is still losing more energy than it is receiving. The most significant of these invisible forces is the air itself. Because we move through it so easily, the atmosphere can feel like a weightless void. In reality, the atmosphere has a total mass of 5 quintillion kilograms. This source from SMHI calculates that every person on Earth has the equivalent of 1 billion kilograms of air associated with them, all pressing down towards the surface. This weight is distributed unevenly. Differences in temperature change the density of the air, creating the massive 3D blocks of high and low pressure seen in these diagrams. Physics dictates that these imbalances cannot persist. The atmosphere constantly moves to shift dense, heavy air into regions of lower pressure, creating the winds we feel at the surface. We track this invisible pressure to predict the weather. When the physical weight of the air drops, as shown on this aneroid barometer, it serves as a reliable indicator that storm systems are moving in. On a continental scale, these pressure differences look like a map of hills and valleys. These 19th century weather charts use curved lines called isobars to visualize the massive pressure gradients that dictate the movement of the wind. Wind is the atmosphere's ongoing attempt to resolve these pressure imbalances, a process of constant redistribution that creates our daily weather. The movement of the tide, the morning frost, and the shifting wind are all parts of the same physical story. They are the results of a planet in a state of continuous physical negotiation, gravity opposing inertia, thermal emission countering solar input, and high pressure balancing against low. This perspective transforms everyday natural events into clear, measurable evidence of planetary scale forces interacting in real time. The stability we experience is the result of these persistent, invisible forces, constantly working to find a balance they will never fully achieve.